Question 1. Benchmark analysis indicates that a network operator is experiencing an issue where specific IP address prefixes, allocated for a particular geographic region, are being advertised by neighboring autonomous systems, ASES, in a manner that suggests suboptimal routing or potential policy violations according to the relevant regulatory framework. To address this, the network administrator needs to influence how these prefixes are routed by external ASES. Which of the following BGP configuration strategies best aligns with regulatory compliance and effective traffic engineering for this scenario? Option A. Disable BGP peering entirely with all ASES located within the affected geographic region. Option B. Configure BGP to prepend the AS path for the affected prefixes when advertising them to neighboring ASES in the specified region. Option C. Modify the local preference attribute for the affected prefixes to a very low value when advertising them to neighboring ASES. Option D. Advertise the affected IP address prefixes without any modifications to their BGP attributes. The correct answer is B. Configure BGP to prepend the AS path for the affected prefixes when advertising them to neighboring ASES in the specified region. Explanation. Scenario analysis. This scenario presents a professional challenge in network operations, where a network administrator must ensure BGP routing policies align with regulatory compliance, specifically concerning the advertisement of IP address space. The challenge lies in interpreting and applying the specific requirements of the relevant regulatory framework, assumed to be US-based for this exam context, as per typical 4A0-102 exam scope, to BGP configurations. Misinterpretation or misapplication can lead to significant compliance violations, service disruptions, and potential penalties. The need for accurate BGP attribute manipulation, particularly as path prepending and community tagging, requires a deep understanding of both BGP mechanics and the regulatory intent behind IP address allocation and routing policies. Correct approach analysis. The correct approach involves meticulously configuring BGP to prepend the AS path for specific prefixes destined for a particular region or customer. This action directly influences BGP's path selection algorithm, making the advertised route less desirable and thus less likely to be chosen by neighboring ASES for traffic originating from that region. This is a standard and effective method for traffic engineering. In this context, aligns with regulatory guidance that may aim to prevent the unauthorized or inefficient use of IP address space by influencing traffic flow away from potentially problematic advertisements. The use of specific BGP communities to tag these routes further aids in policy enforcement and auditing, demonstrating a proactive approach to compliance. This method is professionally sound because it directly addresses the regulatory objective through a well-established BGP mechanism, ensuring control over routing and adherence to policy without violating fundamental BGP principles or regulatory mandates. Incorrect approaches analysis. Advertising the prefixes without any modification to influence path selection is incorrect because it fails to address the regulatory concern of potentially inefficient or unauthorized use of IP address space. This approach neglects the responsibility to actively manage routing policies in accordance with the specified regulatory framework, leaving the network vulnerable to suboptimal traffic paths or potential compliance breaches. Disabling BGP peering with the affected region entirely is an incorrect and overly aggressive approach. While it would prevent the advertisement of the prefixes, it would also sever all legitimate BGP communication with that region, leading to a complete loss of connectivity. This is not a nuanced solution and likely violates broader service level agreements or operational requirements, going far beyond the scope of the specific regulatory concern. Modifying the local preference attribute to a very low value for these prefixes is also an incorrect approach in this specific context. While local preference is a BGP path selection attribute, it is primarily used within an AS to influence inbound traffic. The regulatory concern here is about influencing outbound traffic or the advertisement of prefixes to external ASES, as path prepending is the more appropriate mechanism for influencing how external ASES view and select routes advertised by this AS. Relying solely on local preference for this specific regulatory compliance scenario would be misapplying the tool. Professional reasoning. Professionals should approach such scenarios by first thoroughly understanding the specific regulatory requirements and their implications for BGP routing. This involves consulting official documentation and, if necessary, seeking clarification from regulatory bodies or legal counsel. The next step is to identify the most appropriate BGP configuration techniques that directly address the regulatory objective while maintaining network stability and operational efficiency. This requires a deep understanding of BGP attributes and their impact on path selection. A phased approach to implementation, including thorough testing in a lab environment and careful monitoring post-deployment, is crucial. Professionals should always prioritize solutions that are compliant, effective, and minimally disruptive to ongoing operations. Question 2. Market research demonstrates that network operators are increasingly seeking to optimize BGP route propagation for enhanced network performance and stability. Considering the Alcatel Lucent Border Gateway Protocol 4A0-102 syllabus, which of the following approaches best aligns with regulatory expectations for maintaining a stable and efficient network infrastructure when configuring BGP route advertisement and acceptance? Option A. Relying solely on default BGP settings without any specific tuning for route advertisement. Option B. Configuring extremely short BGP keep-live and hold time timers to detect peer failures rapidly. Option C. Disabling BGP route refresh capabilities to reduce the overhead of route updates. Option D. Implementing next hop self on iBGP peers, ensuring route refresh capabilities are enabled, and utilizing route map policies to control attribute propagation. The correct answer is D. Implementing next hop self on iBGP peers, ensuring route refresh capabilities are enabled, and utilizing route map policies to control attribute propagation. Explanation. Scenario analysis. This scenario presents a professional challenge in network operations where optimizing BGP route propagation is critical for efficient internet traffic management. The challenge lies in balancing the need for rapid convergence and accurate routing information with the potential for network instability and resource exhaustion, if not managed correctly. Professionals must exercise careful judgment to select BGP configuration parameters that align with network policy, performance objectives, and the specific characteristics of the Alcatel Lucent platform, all within the defined regulatory framework for network operations. Correct approach analysis. The correct approach involves a nuanced understanding of BGP timers and their impact on route propagation and network stability. Specifically, tuning the BGP next hop self command in conjunction with appropriate route refresh capabilities and judicious use of route map policies to influence attribute propagation is paramount. This approach represents best professional practice because it directly addresses the core mechanisms of BGP route advertisement and acceptance. By ensuring that BGP speakers correctly advertise their reachability information and that route updates are processed efficiently, this method minimizes the risk of routing black holes or suboptimal path selection. The regulatory framework for network operations, while not explicitly dictating BGP timer values, mandates that network operators ensure the stability, security, and efficient functioning of their networks. This approach directly supports these overarching regulatory objectives by promoting predictable and stable BGP convergence. Incorrect approach is analysis. One incorrect approach is to indiscriminately disable route refresh capabilities. This would be a regulatory and ethical failure because it directly impedes the network's ability to adapt to topology changes or policy updates without requiring a full BGP session reset. This can lead to prolonged periods of routing instability, violating the implicit regulatory requirement for network reliability and availability. Another incorrect approach is to solely rely on aggressive keep-live and hold time timer values without considering the impact on peer stability. While faster detection of failures might seem beneficial, excessively short timers can lead to flapping BGP sessions due to transient network issues or processing delays, causing frequent route recalculations and network churn. This violates the principle of network stability and can be seen as a failure to exercise due diligence in network management, potentially contravening guidelines that emphasize robust and resilient network design. A third incorrect approach is to ignore the implications of next hop self on internal BGP/iBGP route advertisement, leading to routes being advertised with incorrect next hop attributes. This can result in traffic being black-holed or misrouted, directly impacting service availability and potentially violating service level agreements, SLAs, which are often implicitly or explicitly governed by regulatory oversight concerning telecommunications service provision. Professional reasoning. Professionals should approach BGP optimization by first understanding the specific network topology, traffic patterns, and business requirements. They should then consult the Alcatel Lucent platform documentation for best practices and recommended configurations related to BGP timers and route propagation mechanisms. A phased approach to configuration changes, with thorough testing in a lab environment or during scheduled maintenance windows, is crucial. Monitoring network convergence times, BGP session stability, and route table sizes before and after changes is essential for validating the effectiveness of the optimization. Professionals must always consider the potential impact of their configurations on network stability and service availability, ensuring compliance with any applicable telecommunications regulations or industry best practices that emphasize network resilience and performance. Question 3. The risk matrix shows that a proposed BGP policy change to optimize traffic flow carries a high risk of route flapping and suboptimal path selection. Which of the following approaches best mitigates these risks while adhering to operational best practices for network stability? Option A. Conduct thorough pre-change validation in a lab environment, followed by a phased rollout to production with continuous post-change monitoring and a defined rollback plan. Option B. Implement the BGP policy change during off-peak hours to minimize user impact if disruptions occur. Option C. Implement the BGP policy change directly to the entire production network during a scheduled maintenance window. Option D. Apply the BGP policy change to a small subset of edge routers and monitor for immediate issues before proceeding with a full deployment. The correct answer is C. Implement the BGP policy change directly to the entire production network during a scheduled maintenance window. Explanation. Scenario analysis. This scenario presents a professional challenge in network operations where a critical BGP routing policy needs to be updated. The challenge lies in balancing the immediate need for network stability and performance with the potential for unintended consequences arising from a complex BGP configuration change. The risk matrix highlights that while the proposed change aims to improve traffic flow, it also carries a significant risk of route flapping or suboptimal path selection, which could disrupt critical services. This requires careful consideration of the impact on network stability, adherence to established operational procedures, and understanding the underlying BGP mechanisms. Correct approach analysis. The correct approach involves a phased implementation with thorough pre-change validation and post-change monitoring. This aligns with best practices in network engineering and operational integrity, which are implicitly supported by regulatory frameworks emphasizing service availability and reliability. Specifically, a staged rollout, starting with a limited scope or a lab environment, allows for the identification and mitigation of issues before they impact the production network. Comprehensive pre-change validation, including simulation and review of the proposed configuration against established routing policies and RFC standards, ensures that the change is technically sound. Post-change monitoring, utilizing BGP-specific tools and performance metrics, is crucial for detecting any deviations from expected behavior and enabling rapid rollback if necessary. This methodical approach minimizes the risk of service disruption, thereby upholding the implicit regulatory expectation of maintaining a stable and reliable network infrastructure. Incorrect approach is analysis. Implementing the change directly to the entire production network without prior validation or a phased rollout represents a significant regulatory and ethical failure. This approach disregards the principle of due diligence in network operations, which is fundamental to ensuring service continuity. Such an action could lead to widespread service outages, violating implicit obligations to maintain network stability and potentially contravening service-level agreements, SLAs, that are often subject to regulatory oversight. Applying the change without a rollback plan is another critical failure. Network changes, especially those involving BGP, are inherently complex and prone to unforeseen issues. The absence of a rollback strategy demonstrates a lack of preparedness and a disregard for the potential negative impact on network operations. This failure to plan for contingencies directly contradicts the best practice of risk mitigation and could result in prolonged service disruption, which would be viewed unfavorably from a regulatory and operational perspective. Performing the change during peak traffic hours, even with some validation, introduces unnecessary risk. While the intention might be to minimize the impact on non-peak users, peak hours are precisely when network stability is most critical. Disruptions during these times have the most severe consequences for users and businesses. This approach prioritizes convenience over robust risk management, failing to adhere to the principle of minimizing operational impact on critical services. Professional reasoning. Professionals should approach network changes, particularly those involving BGP, by first conducting a thorough risk assessment. This involves understanding the potential impact of the change on network stability, performance, and service availability. The next step is to develop a detailed implementation plan that includes pre-change validation, a phased rollout strategy, and a comprehensive rollback plan. This plan should be reviewed by peers and stakeholders to ensure all potential risks have been considered. During implementation, continuous monitoring is essential to detect any anomalies. If issues arise, the rollback plan should be executed immediately. This systematic and risk-averse approach ensures that network changes are implemented safely and effectively, minimizing disruption and maintaining service integrity. Question 4. Risk assessment procedures indicate that an IXP BGP peering session is experiencing intermittent packet loss and route flapping, impacting service for a significant customer segment. Which of the following diagnostic and remediation approaches best adheres to operational best practices for maintaining network stability and minimizing service disruption? Option A. Conduct a phased diagnostic approach, starting with log analysis and passive monitoring, escalating to carefully scheduled, low-impact BGP diagnostic commands if necessary, and only considering session resets or reconfigurations after thorough analysis and risk assessment. Option B. Disable the IXP peering session entirely to prevent further instability and address the issue during a scheduled maintenance window. Option C. Perform a full BGP resynchronization across all active peering sessions to ensure consistency throughout the routing infrastructure. Option D. Immediately initiate a BGP reset command on the affected peering session to force a re-establishment of the connection. The correct answer is D. Immediately initiate a BGP reset command on the affected peering session to force a re-establishment of the connection. Explanation. Scenario analysis. This scenario presents a challenge in network operations where a critical BGP peering session with a major Internet Exchange Point (IXP) is experiencing intermittent instability. The core difficulty lies in balancing the immediate need for network stability and service continuity with the requirement for thorough, non-disruptive troubleshooting. A hasty or poorly planned intervention could exacerbate the problem, leading to widespread connectivity issues for customers and potential reputational damage. The pressure to restore service quickly must be tempered by adherence to established operational procedures and the potential impact on the broader Internet ecosystem. Correct approach analysis. The correct approach involves a systematic, phased investigation that prioritizes non-disruptive methods. This aligns with best practices for network management and operational integrity, particularly concerning critical infrastructure like BGP. By first analyzing existing logs and monitoring data, network engineers can gather initial insights without impacting the live network. If further investigation is needed, employing passive monitoring tools or scheduled, low-impact diagnostic commands during off-peak hours minimizes the risk of service disruption. This methodical approach ensures that any changes or tests are controlled, documented, and have a reduced likelihood of causing collateral damage. This reflects a professional commitment to maintaining network stability and adhering to operational guidelines that prioritize service availability and minimize risk. Incorrect approaches analysis. Immediately initiating aggressive BGP reset commands without prior analysis is a failure of professional judgment and operational best practice. Such an action bypasses the crucial diagnostic steps, increasing the likelihood of unintended consequences, such as flapping routes or broader network instability. This approach disregards the principle of least privilege and controlled change management, potentially violating internal operational policies and industry standards for network maintenance. Implementing a full BGP resynchronization across all peering sessions, including those not directly affected by the IXP issue, represents an overreach and a failure to apply targeted troubleshooting. This broad-stroke approach is inefficient and significantly increases the risk of widespread disruption, impacting services beyond the immediate problem area. It demonstrates a lack of understanding of the scope of the issue and a disregard for the principle of minimizing impact. Disabling the IXP peering session entirely as a first step, without attempting to diagnose the root cause, is an extreme measure that should only be considered as a last resort. This action immediately severs a critical connectivity path, causing significant service degradation for customers relying on that peering. It signifies a failure to exhaust less disruptive diagnostic options and a premature escalation that prioritizes immediate disconnection over controlled problem solving. Professional reasoning. Professionals facing such a scenario should employ a structured decision-making process. This begins with a thorough understanding of the network's architecture and the criticality of the affected peering. The first step is always to leverage existing monitoring and logging systems to gather as much information as possible without impacting the live environment. If the issue persists, the next phase involves planning and executing diagnostic steps with the lowest possible impact, such as passive observation or carefully scheduled, minimal-impact commands. Any changes to the BGP configuration or state should be meticulously documented, reviewed, and, where possible, tested in a lab environment or during scheduled maintenance windows. The decision to escalate or implement more drastic measures should be based on a clear assessment of risk versus reward, with a strong emphasis on preserving service continuity. Question 5. The evaluation methodology shows that when an Alcatel Lucent router receives multiple BGP paths to the same destination prefix from different neighbors, the router must select the best path to install in the routing table. Considering the standard BGP path selection algorithm and the need for network stability and predictability, which of the following approaches represents the most robust and professionally sound method for determining the best path in a typical interdomain routing scenario? Option A. Select the path with the highest locally configured BGP community value. Option B. Choose the path that was received first from any BGP neighbor. Option C. Prioritize the path with the shortest as path attribute. Option D. Favor the path advertised by the neighbor with the highest IP address. The correct answer is C. Prioritize the path with the shortest as path attribute. Explanation. The evaluation methodology shows that network engineers must make critical decisions regarding BGP route selection when faced with multiple paths to a destination. This scenario is professionally challenging because an incorrect route selection can lead to suboptimal network performance, increased latency, service disruption, and potential financial penalties if service-level agreements (SLAs) are breached. The pressure to maintain network stability and efficiency, coupled with the complexity of BGP attributes, demands a systematic and informed decision-making process. The correct approach, prioritizing the as-path attribute for route selection, represents best professional practice because it directly aligns with the fundamental design principles of BGP. As-path is a well-established and universally understood metric that promotes loop prevention and allows for policy-based routing decisions based on the number of autonomous systems traversed. Adhering to this standard attribute ensures predictable and stable routing behavior, which is crucial for maintaining network integrity and meeting operational objectives. This aligns with the implicit regulatory expectation of maintaining a stable and functional network infrastructure. An incorrect approach that prioritizes a locally significant but non-standard attribute, such as a custom BGP community value that is not universally interpreted or enforced across peer access, represents a significant regulatory and ethical failure. This is because it introduces unpredictability into the global routing table. Other networks may not understand or respect this custom attribute, leading to routing loops, black holes, or suboptimal path selection from their perspective. This violates the ethical responsibility to contribute to a stable and interoperable internet ecosystem. Furthermore, relying on such an attribute could be seen as a failure to adhere to industry best practices and established routing protocols, potentially leading to non-compliance with implicit operational standards. Another incorrect approach that ignores all BGP attributes and defaults to the first received route from a peer can lead to unpredictable and potentially malicious routing. This is ethically unsound as it abdicates responsibility for informed decision-making and opens the network to manipulation by peers. It fails to uphold the professional duty to ensure the security and reliability of network traffic. The professional reasoning framework for such situations should involve a clear understanding of BGP's attribute hierarchy and the intended purpose of each attribute. Engineers should first consider attributes that promote stability and loop prevention, like as path, then attributes that allow for policy enforcement, like local pref and med, if applicable and understood by peers, and finally, attributes that provide more granular control or information. A systematic evaluation of available paths against defined network policies and the established BGP decision process is paramount. When in doubt, consulting network documentation, peer agreements, and seeking input from experienced colleagues is essential to ensure informed and responsible routing decisions. Question 6. The monitoring system demonstrates a recurring BGP session flap with a specific external peering router. The alert indicates that the BGP session between your network and the peer is repeatedly going down and then re-establishing. What is the most appropriate initial course of action to diagnose and resolve this issue? Option A. Immediately reset the BGP session on your router and monitor for recurrence. Option B. Assume the issue is with the peer router and focus solely on verifying your router's BGP configuration against established standards. Option C. Examine BGP logs on your router for specific error messages, check interface statistics for errors or drops, and review recent configuration changes on your router that might affect BGP neighbor relationships. Option D. Implement a temporary adjustment to BGP timers, such as increasing the hold time, to stabilize the session while further investigation occurs. The correct answer is A. Immediately reset the BGP session on your router and monitor for recurrence. Explanation. Scenario analysis. This scenario presents a professional challenge due to the critical nature of BGP routing stability and the potential for cascading failures across interconnected networks. The monitoring system's alert, indicating a BGP session flap with a specific peer, requires immediate and accurate diagnosis. Failure to correctly identify the root cause can lead to prolonged network instability, service degradation for end users, and potential breaches of service-level agreements, SLAs. The challenge lies in distinguishing between transient network anomalies, configuration errors, or more systemic issues that could impact multiple peering sessions. The need for swift resolution, while maintaining network integrity and adhering to operational best practices, demands a methodical and informed approach. Correct approach analysis. The correct approach involves a systematic investigation that begins with verifying the BGP session status and examining the BGP logs on both the local router and, if possible, the peer router. This includes checking for specific error messages related to session establishment, keep-alives, or route advertisements. The next step is to analyze the router's interface statistics for errors, packet drops, or high utilization that might indicate underlying physical or link layer issues. Concurrently, checking for recent configuration changes on the local router that could affect BGP neighbor relationships or policies is crucial. This methodical, evidence-based approach directly aligns with the operational principles of network management and troubleshooting, emphasizing data-driven decision-making to isolate the problem. It prioritizes understanding the immediate cause of the flap before implementing any corrective actions, thereby minimizing the risk of introducing new problems. This aligns with the implicit regulatory expectation of maintaining reliable network services. Incorrect approaches analysis. One incorrect approach is to immediately reset the BGP session without further investigation. This is professionally unacceptable because it bypasses the diagnostic process. It fails to identify the root cause, meaning the underlying issue will likely persist and cause further flaps. This reactive measure can mask critical problems, such as a faulty interface or a misconfiguration on the peer, leading to repeated incidents and potential SLA violations. Ethically, it represents a failure to exercise due diligence in network management. Another incorrect approach is to assume the issue is with the peer router and to only focus on local router configurations. This is a premature conclusion that ignores potential local factors. If the problem lies with the local router's interface, hardware, or a local configuration error, focusing solely on the peer will be unproductive and delay resolution. This demonstrates a lack of comprehensive troubleshooting, which is a failure in professional responsibility to thoroughly investigate all potential causes. A third incorrect approach is to immediately implement a broad policy change to mitigate the perceived instability, such as reducing the frequency of BGP updates or increasing hold timers, without understanding the specific reason for the flap. While these actions might temporarily mask the symptom, they do not address the root cause and could negatively impact routing convergence or the effectiveness of BGP policy enforcement. This approach prioritizes a quick fix over a sustainable solution and demonstrates a lack of understanding of the implications of BGP parameter tuning, potentially leading to unintended network consequences. Professional reasoning. Professionals should approach such alerts by adopting a structured troubleshooting methodology. This involves 1. Information gathering. Collect all available data including system logs, BGP state, interface statistics, and recent configuration changes. 2. Hypothesis generation. Formulate potential causes for the BGP session flap based on the gathered information. 3. Hypothesis testing. Systematically test each hypothesis by examining specific logs, configurations, and network conditions. 4. Root cause identification. Pinpoint the definitive cause of the issue. 5. Resolution. Implement the most appropriate fix, prioritizing solutions that address the root cause and minimize disruption. 6. Verification. Confirm that the issue is resolved and monitor for recurrence. This iterative process ensures that actions are informed, targeted, and effective, upholding professional standards of network reliability and service delivery. Question 7. The control framework reveals a scenario where a new BGP routing policy needs to be implemented across a geographically dispersed network infrastructure managed by Alcatel Lucent routers. The policy aims to influence outbound traffic steering to specific peering points based on real-time network conditions. Given the critical nature of BGP for internet connectivity, what is the most professionally responsible approach to deploy this new policy to minimize disruption and ensure compliance with operational best practices? Option A. Implement the new BGP routing policy simultaneously across all affected routers after a thorough review of the configuration syntax. Option B. Manually configure the new BGP routing policy on each router individually, relying on the experience of senior engineers to avoid errors. Option C. Apply the new BGP routing policy immediately to all routers to ensure consistent traffic steering as quickly as possible, assuming the configuration has been tested in a lab environment. Option D. Deploy the new BGP routing policy incrementally, starting with a small subset of non-critical routers, followed by phased rollout to the rest of the network with continuous monitoring and validation at each stage. The correct answer is A. Implement the new BGP routing policy simultaneously across all affected routers after a thorough review of the configuration syntax. Explanation. The control framework reveals a common implementation challenge in large-scale BGP deployments, ensuring consistent and predictable routing behavior across diverse network segments while adhering to strict operational guidelines. This scenario is professionally challenging because network engineers must balance the immediate need for connectivity with the long-term implications of routing policy misconfigurations. The potential for widespread service disruption, security vulnerabilities, and non-compliance with service-level agreements, SLAs, necessitates a meticulous and well-reasoned approach. The correct approach represents best professional practice because it prioritizes a systematic and verifiable method for policy deployment. By leveraging a staged rollout and thorough validation, engineers minimize the risk of introducing unintended consequences. This aligns with professional ethical obligations to maintain network stability and service availability. Furthermore, it demonstrates due diligence in adhering to operational best practices, which are often implicitly or explicitly mandated by industry standards and organizational policies that govern network operations. An incorrect approach that involves immediate, widespread deployment without prior testing fails to uphold professional responsibility. This can lead to cascading failures, impacting numerous customers and potentially violating contractual obligations, SLAs. Such an action would represent a significant ethical lapse, prioritizing speed over safety and reliability. Another incorrect approach, focusing solely on immediate connectivity without considering the long-term impact of the chosen policy, overlooks the importance of sustainable network design. This can result in suboptimal routing, increased latency, and potential security risks, all of which are professionally unacceptable. A third incorrect approach, relying on manual configuration without any form of automation or validation, is prone to human error. This increases the likelihood of misconfigurations, leading to unpredictable routing and potential outages, which is a failure of professional diligence. Professionals should employ a decision-making framework that emphasizes risk assessment, phased implementation, and continuous monitoring. This involves understanding the potential impact of any change, planning for rollback scenarios, and thoroughly testing configurations in a controlled environment before deploying them to production. The decision to implement a routing policy should be driven by a clear understanding of its objectives and a comprehensive plan to achieve them safely and effectively. Question 8. Assessment of the potential impact of a proposed BGP policy modification on network reachability and stability, considering the need for a controlled and verifiable implementation. Option A. Immediately revert the BGP policy change if any minor routing instability is detected post-implementation, without further investigation into the cause. Option B. Conduct a comprehensive pre-change impact analysis using network simulation tools and a staged rollout to a subset of network devices before full production deployment. Option C. Implement the BGP policy change directly on the production network during a scheduled maintenance window with a predefined rollback plan in place. Option D. Deploy the BGP policy change during the busiest network traffic hours to observe its behavior under maximum load. Correct answer is C. Implement the BGP policy change directly on the production network during a scheduled maintenance window with a predefined rollback plan in place. Explanation. Scenario analysis. This scenario presents a professional challenge in network operations where a critical BGP routing policy change is proposed. The challenge lies in accurately assessing the potential impact of this change on network stability and reachability without causing an outage. Network engineers must balance the need for policy optimization with the imperative to maintain service continuity for all users and connected networks. The complexity arises from the interconnected nature of BGP, where a seemingly minor change can have cascading effects across multiple autonomous systems. Careful judgment is required to anticipate unintended consequences and ensure the proposed change aligns with operational best practices and any relevant service level agreements. SLAs. Correct approach analysis. The correct approach involves a phased, controlled deployment strategy that includes thorough pre-change analysis and post-change monitoring. This best professional practice is justified by the fundamental principle of network stability and reliability, which is paramount in BGP operations. Regulatory and ethical considerations mandate that network operators act with due diligence to prevent service disruption. A controlled deployment, often involving a pilot or staged rollout, allows for the observation of the change's behavior in a live environment without affecting the entire network. This aligns with the implicit expectation of service providers to maintain a stable and predictable routing environment, as often stipulated in industry standards and customer contracts. Incorrect approach is analysis. Implementing the change directly on the production network without prior simulation or a staged rollout represents a significant regulatory and ethical failure. This approach disregards the potential for widespread service disruption, which could lead to breaches of SLAs, financial penalties, and reputational damage. It demonstrates a lack of due diligence and a failure to adhere to the principle of least impact. Rolling back the change immediately after deployment without sufficient analysis of the root cause of any observed issues is also professionally unsound. While rollback is a necessary contingency, failing to analyze the cause prevents learning and future prevention, potentially leading to repeated problems. This approach suggests a reactive rather than proactive operational stance, which is not conducive to long-term network health and stability. Performing the change during a peak traffic period, even with a rollback plan, is highly risky. This increases the probability of encountering unforeseen issues under load, exacerbating any negative impact and making troubleshooting more difficult. It demonstrates a disregard for the operational impact on users and other network participants, which is a failure in professional responsibility. Professional reasoning. Professionals should adopt a systematic approach to network changes. This involves 1. Understanding the proposed change and its intended outcome. 2. Conducting thorough impact analysis using network simulation tools and historical data. 3. Developing a detailed deployment plan including rollback procedures. 4. Communicating the plan change to all relevant stakeholders. 5. Executing the change in a controlled manner, preferably during a maintenance window or in a phased approach. 6. Closely monitoring network performance and BGP convergence post-change. 7. Analyzing any anomalies and taking corrective actions as needed. 8. Documenting the entire process and lessons learned. Question 9. Benchmark analysis indicates that a recent regulatory update in the specified jurisdiction mandates stricter controls on the advertisement of specific IP prefixes via BGP to prevent unauthorized traffic redirection. An Alcatel Lucent router administrator is tasked with ensuring the network's BGP configuration adheres to these new requirements. Which of the following approaches best aligns with regulatory compliance and professional responsibility? Option A. Postpone the configuration changes until a more opportune time, citing the complexity of the regulatory update and the potential for operational disruption, while continuing to monitor for any enforcement actions. Option B. Prioritize implementing BGP configuration changes based on the latest Alcatel Lucent best practice guides for route filtering, assuming these implicitly cover regulatory mandates. Option C. Proactively consult the official regulatory documentation and any associated implementation guidelines provided by the governing body, and then meticulously map these requirements to specific Alcatel Lucent BGP configuration commands, seeking expert clarification if any aspect of the regulation is ambiguous. Option D. Rely on informal discussions with network engineering peers in other organizations to understand how they are interpreting and implementing similar regulatory changes, and apply those learned techniques to the Alcatel Lucent BGP configuration. The correct answer is B. Prioritize implementing BGP configuration changes based on the latest Alcatel Lucent best practice guides for route filtering, assuming these implicitly cover regulatory mandates. Explanation. The scenario presents a common challenge in network operations, ensuring compliance with evolving regulatory requirements for network traffic management, specifically concerning the advertisement of routes via BGP. The professional challenge lies in interpreting and applying these regulations to the practical configuration and operation of an Alcatel Lucent BGP implementation, without introducing service disruptions or security vulnerabilities. The need for careful judgment stems from the potential impact of misconfiguration on inter-as routing stability and adherence to traffic engineering policies mandated by regulatory bodies. The correct approach represents best professional practice because it prioritizes a thorough understanding of the specific regulatory framework governing BGP operations within the relevant jurisdiction. This involves consulting official documentation, seeking clarification from regulatory bodies when ambiguities exist, and validating proposed configurations against these requirements before deployment. This proactive and informed methodology minimizes the risk of noncompliance, which could lead to penalties, reputational damage, and operational instability. It aligns with the ethical obligation to operate networks responsibly and in accordance with established legal and technical standards. An incorrect approach that focuses solely on vendor-specific best practices without considering the overarching regulatory mandate is professionally unacceptable. This failure stems from a misunderstanding of the hierarchy of operational requirements. Vendor best practices are guidelines, whereas regulatory compliance is a legal obligation. Such an approach risks violating specific jurisdictional rules, even if the network appears to be functioning optimally from a technical standpoint. Another incorrect approach, which involves implementing changes based on anecdotal evidence or peer recommendations without independent verification against regulatory requirements, is also professionally flawed. This introduces an unacceptable level of risk, as informal advice may not accurately reflect the specific legal obligations or may be outdated. It bypasses the due diligence necessary to ensure compliance and could lead to unintended regulatory breaches. Finally, an approach that delays or ignores regulatory updates due to perceived operational complexity is ethically and professionally negligent. The responsibility to stay informed and adapt network operations to comply with current regulations is paramount. Failure to do so can result in significant legal and financial repercussions for the organization and the individuals responsible. The professional decision-making process for similar situations should involve a structured approach. 1. Identify the relevant regulatory framework and specific requirements pertaining to BGP operations. 2. Conduct a gap analysis between current BGP configurations and the identified regulatory requirements. 3. Consult official regulatory guidance and, if necessary, seek clarification from the governing body. 4. Develop and test configuration changes in a controlled environment to ensure compliance and operational stability. 5. Document all changes, justifications, and compliance verification steps. 6. Implement changes with a rollback plan and monitor network behavior closely post-implementation. Question 10. To address the challenge of ensuring Alcatel Lucent BGP configurations comply with new regulatory directives on traffic filtering and routing policy enforcement, which of the following represents the most professionally sound and compliant approach? Option A. Immediately implement the new filtering rules based on a general understanding of the regulatory text, assuming the vendor's default BGP security features will adequately address the requirements. Option B. Engage with the regulatory body to seek clarification on ambiguous aspects of the directives, develop a detailed technical implementation plan, and conduct comprehensive testing in a lab environment before a staged rollout. Option C. Apply the new filtering rules broadly across all BGP peering sessions, without specific analysis of individual peering agreements or traffic flows, based on a literal, unverified interpretation of the regulatory text. Option D. Prioritize other network upgrades and postpone the implementation of the new BGP filtering rules until a later date when resources are more readily available, assuming the current configuration does not pose an immediate, obvious risk. The correct answer is A. Immediately implement the new filtering rules based on a general understanding of the regulatory text, assuming the vendor's default BGP security features will adequately address the requirements. Explanation. The scenario presents a common challenge in network operations, ensuring compliance with evolving regulatory requirements for network traffic management, specifically concerning BGP routing policies. A professional challenge lies in interpreting and implementing these regulations within the technical constraints of Alcatel Lucent BGP configurations, without introducing service disruptions or security vulnerabilities. The need for deep understanding of both the regulatory framework and the BGP protocol's operational nuances is paramount. The correct approach represents best professional practice because it prioritizes a thorough, documented, and tested implementation strategy. This aligns with the principles of due diligence and risk management inherent in regulatory compliance. By engaging with the regulatory body for clarification and conducting rigorous testing in a controlled environment, the network operator demonstrates a commitment to accurate implementation and minimizes the risk of non-compliance or operational impact. This proactive and meticulous method is essential for maintaining network integrity and adhering to legal obligations. An incorrect approach that involves immediate, untested implementation of a broad interpretation of the regulation fails to account for potential misinterpretations or unintended consequences. This could lead to a violation of the regulation if the implementation is technically flawed or if the interpretation was incorrect. Ethically, it demonstrates a lack of due care. Another incorrect approach, which involves ignoring the regulation due to perceived complexity or resource constraints, is a direct violation of legal and ethical obligations. This negligence can result in significant penalties and reputational damage. A third incorrect approach, relying solely on vendor default configurations without verifying their alignment with specific regulatory mandates, is insufficient. While vendors may aim for compliance, specific regional or operational requirements often necessitate custom configurations, and assuming defaults are adequate is a failure of professional responsibility. Professionals should approach such situations by first seeking to fully understand the regulatory requirements, engaging with the issuing authority if ambiguity exists. This should be followed by a detailed technical assessment of how these requirements translate into BGP configuration changes. A phased implementation plan, including lab testing and staged rollouts with rollback capabilities, is crucial. Continuous monitoring and auditing post-implementation are also vital to ensure ongoing compliance and operational stability. Question 11. The monitoring system demonstrates a specific BGP prefix is experiencing intermittent route flapping, being advertised and then withdrawn repeatedly from a particular neighbor. What is the most appropriate initial diagnostic step to isolate the cause of this instability? Option A. Adjust the BGP keep-alive and hold timers for the neighbor to a more aggressive setting. Option B. Escalate the issue to the remote peers network operations center without performing local diagnostics. Option C. Examine the BGP logs for the affected neighbor and analyze the specific BGP attributes of the flapping route, paying close attention to any policy-related attributes or as path changes. Option D. Immediately disable the BGP peering session with the neighbor to prevent further instability. The correct answer is C. Examine the BGP logs for the affected neighbor and analyze the specific BGP attributes of the flapping route, paying close attention to any policy-related attributes or as path changes. Explanation: scenario analysis. This scenario presents a common implementation challenge in BGP routing: unexpected route flapping. The professional challenge lies in accurately diagnosing the root cause of the flapping without disrupting legitimate traffic or introducing further instability. The pressure to restore service quickly can lead to hasty decisions. Furthermore, understanding the nuances of BGP path selection and the impact of various configuration parameters is critical. The regulatory framework for this exam: 4A0-102 Alcatel Lucent Border Gateway Protocol implicitly emphasizes network stability and adherence to best practices for interdomain routing, which are foundational for reliable internet connectivity. Failure to address route flapping promptly and effectively can lead to service degradation, impacting end users and potentially violating service-level agreements, SLAs. If such agreements are in place, though specific regulatory penalties are not detailed in the exam scope beyond the technical requirements. Correct approach analysis. The correct approach involves a systematic, evidence-based investigation. This begins with verifying the BGP session status and examining the specific attributes of the flapping routes. Analyzing the BGP logs for the affected neighbor, looking for specific error messages or frequent update/withdraw messages, is paramount. The next step is to inspect the inbound and outbound policies applied to the neighbor, specifically focusing on route maps, prefix lists, and as path filters that might be causing the route to be advertised and then withdrawn repeatedly due to policy misconfiguration or dynamic changes. This methodical approach ensures that the problem is addressed at its source, minimizing the risk of unintended consequences. It aligns with the implicit regulatory expectation of maintaining stable and predictable routing, which is a cornerstone of BGP's function in the global internet. Incorrect approaches analysis. One incorrect approach is to immediately disable the BGP neighbor. This is a blunt instrument that, while stopping the flapping, also severs all legitimate routing information exchange with that peer. This can lead to significant traffic blackholing or suboptimal routing for a large number of prefixes, causing widespread service disruption. Ethically, this is a failure to exercise due diligence in troubleshooting and to minimize impact. Another incorrect approach is to indiscriminately adjust BGP timers, e.g., hold timers, keep-alive timers, without understanding the specific cause of the flapping. This is akin to treating symptoms rather than the disease and can lead to session instability or even more severe routing issues. It demonstrates a lack of understanding of BGP's state machine and the implications of altering its fundamental operational parameters. A third incorrect approach is to assume the issue is with the remote peer and to escalate without performing thorough local diagnostics. This wastes valuable time and resources and fails to acknowledge the possibility of a misconfiguration on the local device, which is often the case. This can lead to delays in resolution and a failure to meet professional responsibilities for network uptime. Professional reasoning. Professionals facing such a challenge should adopt a structured troubleshooting methodology. This involves 1. Defining the problem clearly: route flapping observed on specific prefixes to a particular neighbor. 2. Gathering information: BGP session status, logs, route attributes. 3. Forming hypotheses: policy misconfiguration, hardware issue, remote peer problem. 4. Testing hypotheses systematically, examining policies, checking logs, verifying peer configuration. 5. Implementing the solution. And 6. Verifying the resolution and monitoring for recurrence. This iterative process, grounded in understanding the BGP protocol and its operational context, is essential for effective and responsible network management. Question 12. Stakeholder feedback indicates a desire to leverage advanced BGP features for enhanced network performance and resilience, but concerns have been raised about the potential impact on current network stability. As the network administrator responsible for the Alcatel Lucent Border Gateway Protocol implementation, which approach best balances these competing interests while adhering to best practices for network change management. Option A. Immediately implement the new BGP features across all network devices to realize the benefits as quickly as possible. Option B. Deploy the new BGP features on a limited number of non-critical edge routers to gauge their performance before considering wider deployment. Option C. Defer the implementation of the new BGP features indefinitely until all potential risks are completely eliminated, which may be an unrealistic goal. Option D. Conduct comprehensive lab testing of the new BGP features in an environment that accurately simulates the production network, followed by a phased rollout to production with continuous monitoring. The correct answer is D. Conduct comprehensive lab testing of the new BGP features in an environment that accurately simulates the production network, followed by a phased rollout to production with continuous monitoring. Explanation: scenario analysis. This scenario presents a professional challenge stemming from conflicting stakeholder priorities regarding network stability and the introduction of new BGP features. The network administrator must balance the immediate need for a stable, predictable network with the strategic imperative to leverage advanced BGP capabilities for improved routing efficiency and resilience. The challenge lies in making a decision that satisfies diverse operational and business objectives, while adhering to established network engineering best practices and any applicable regulatory guidelines for network operation and security. The inherent risk of introducing changes to a critical routing protocol, like BGP, necessitates a rigorous and well-justified decision-making process. Correct approach analysis. The correct approach involves a phased, controlled implementation of the new BGP features, preceded by thorough testing in a lab environment that accurately mirrors the production network's configuration and traffic patterns. This methodology represents best professional practice because it systematically mitigates risk. Regulatory compliance, particularly concerning network availability and security, is implicitly supported by this approach. By validating functionality and performance in isolation, the administrator ensures that the new features do not negatively impact existing services or introduce vulnerabilities. This aligns with the principle of due diligence in network management, aiming to prevent service disruptions and maintain the integrity of the network infrastructure. Incorrect approaches analysis. Implementing the new BGP features directly into the production environment without prior testing is a significant regulatory and ethical failure. It demonstrates a disregard for network stability and service availability, potentially violating service-level agreements, SLAs, and exposing the organization to operational and financial risks. This approach also fails to adhere to the principle of least privilege and robust change management, which are fundamental to secure and reliable network operations. Rolling back the BGP configuration to a previous stable state and indefinitely delaying the implementation of the new features, while seemingly safe, represents a failure to innovate and adapt. This can lead to missed opportunities for network optimization and resilience, potentially impacting the organization's competitive edge and ability to meet evolving business demands. Ethically, it may represent a failure to proactively manage the network for future needs. Implementing the new BGP features only on a subset of edge routers without a comprehensive understanding of their impact on the core routing infrastructure is also a flawed approach. This can lead to unpredictable routing behavior, suboptimal path selection, and potential instability as BGP states converge across different parts of the network. It lacks the systematic risk assessment required for critical infrastructure changes and could inadvertently create new points of failure or security vulnerabilities. Professional reasoning. Professionals facing such a decision should employ a structured decision-making framework. This typically involves 1. Problem definition. Clearly articulate the need for the new BGP features and the associated risks. 2. Information gathering. Collect data on the proposed features, their impact, and available testing resources. 3. Option generation. Brainstorm potential implementation strategies, including phased rollouts, lab testing, and pilot programs. 4. Option evaluation. Assess each option against criteria such as risk, cost, time to implement, and potential benefits, considering regulatory and operational impacts. 5. Decision-making. Select the option that best balances benefits and risks with a strong emphasis on stability and security. 6. Implementation and monitoring. Execute the chosen plan with meticulous attention to detail and continuous monitoring. 7. Review and feedback. Evaluate the outcome and incorporate lessons learned into future decisions. Question 13. Consider a scenario where a network engineer is tasked with implementing a new BGP policy on Alcatel Lucent edge routers to influence outbound traffic path selection for specific prefixes. The policy is designed to leverage as path prepending to make certain paths less attractive to neighboring autonomous systems. The engineer has a strong understanding of the policy's intended effect on traffic flow, but is aware that BGP policy changes can have complex and sometimes unforeseen interactions with existing configurations and the broader routing table. The engineer needs to decide on the most prudent approach for deploying this policy to minimize disruption and ensure the integrity of routing information. Option A. Conduct a thorough lab simulation of the proposed as-path prepending policy using a representative network topology and traffic patterns before any production deployment. Following successful lab testing, deploy the policy incrementally to a small subset of edge routers, closely monitoring BGP neighbor states and routing table stability before expanding the deployment. Option B. Implement the as-path prepending policy on all edge routers, but focus solely on verifying that the specific prefixes are now taking the desired outbound path, without actively monitoring for any broader routing table instability or impact on other prefixes. Option C. Apply the as-path prepending policy to a limited set of edge routers without prior lab testing, assuming that the limited scope will contain any potential negative impacts. Option D. Implement the as-path prepending policy directly on all edge routers simultaneously, relying on the engineer's confidence in the policy's design to avoid issues. The correct answer is D. Implement the as-path prepending policy directly on all edge routers simultaneously, relying on the engineer's confidence in the policy's design to avoid issues. Explanation. Scenario analysis. This scenario presents a professional challenge in network engineering, where a critical BGP routing policy needs to be implemented. The challenge lies in balancing the immediate need for network stability and performance with the long-term implications of policy design, particularly concerning the potential for unintended consequences and the adherence to established best practices. The engineer must make a decision that is technically sound, operationally efficient, and compliant with the implicit regulatory framework of maintaining a stable and predictable internet routing environment, even without explicit governmental regulations dictating BGP policy specifics. The complexity arises from the interconnected nature of BGP and the ripple effects a misconfigured policy can have across multiple autonomous systems. Correct approach analysis. The correct approach involves a phased implementation and rigorous testing strategy. This aligns with best professional practices in network operations, which prioritize minimizing risk and ensuring service continuity. By first testing the policy in a lab environment that accurately simulates the production network, the engineer can identify potential issues without impacting live traffic. Subsequently, a controlled rollout to a subset of edge routers, followed by monitoring, allows for verification of the policy's intended behavior and detection of any unforeseen side effects. This iterative approach, grounded in principles of change management and risk mitigation, is crucial for maintaining the integrity and predictability of BGP routing, which is fundamental to the operational stability of the Internet. This implicitly adheres to the spirit of any regulatory framework that mandates reliable network operation and service availability. Incorrect approaches analysis. Implementing the policy directly on all edge routers without prior testing or a phased rollout represents a significant regulatory and ethical failure. It demonstrates a disregard for operational stability and service availability, which are implicitly expected by users and other network operators. This approach significantly increases the risk of widespread routing disruptions, potentially impacting critical services and leading to financial losses or reputational damage. It violates the professional responsibility to implement changes in a controlled and predictable manner. Implementing the policy only on a subset of routers, but without a lab simulation first, is also professionally unsound. While it introduces some level of control, it omits a crucial step in identifying fundamental design flaws or incompatibilities that could manifest even in a limited live deployment. This approach still carries a higher risk of unintended consequences compared to a comprehensive lab test, potentially leading to suboptimal routing or instability that requires immediate and disruptive remediation. Focusing solely on the immediate performance gains without considering the potential for route flapping or the impact on neighboring ASNs is another failure. BGP is a complex protocol where local optimizations can have global repercussions. A responsible network engineer must consider the broader impact of their policies, ensuring they do not negatively affect the routing stability of the wider internet. This approach prioritizes short-term benefits over long-term network health and inter-OS cooperation, which are essential for the functioning of the global routing system. Professional reasoning. Professionals should employ a structured decision-making framework that prioritizes risk assessment and mitigation. This involves 1. Understanding the objective, clearly define the desired outcome of the BGP policy. 2. Identifying potential risks, analyze all possible negative consequences of the proposed change. 3. Developing mitigation strategies, plan steps to prevent or minimize identified risks. 4. Phased implementation and testing, employ a controlled rollout, starting with simulations and progressing to live environments with monitoring. 5. Continuous monitoring and evaluation. Regularly assess the policy's performance and impact. This framework ensures that changes are made responsibly, maintaining network stability and adhering to professional standards of care. Question 14. Upon reviewing a proposed BGP policy modification intended to optimize traffic flow to a new data center, which approach best ensures network stability and minimizes the risk of service disruption, considering the potential for unintended consequences on existing routing? Option A. Implement the change directly in the production environment during a scheduled maintenance window, relying on the vendor's documentation for guidance. Option B. Proceed with the change immediately after a brief discussion with a senior engineer, as the urgency to connect to the new data center is high. Option C. Apply the proposed BGP policy change to a small segment of the network and monitor for a short period before rolling it out to the entire infrastructure without extensive lab testing. Option D. Conduct a thorough impact analysis, perform comprehensive testing in a lab environment, and then implement the change in a staged rollout across the network with continuous monitoring. Correct answer is A. Implement the change directly in the production environment during a scheduled maintenance window, relying on the vendor's documentation for guidance. Explanation. Scenario analysis. This scenario presents a common challenge in network operations where a critical BGP routing policy change is proposed. The challenge lies in balancing the immediate need for network optimization or security with the potential for widespread disruption. Network engineers must consider the impact of their decisions on service availability, customer experience, and adherence to operational best practices, all within the context of the Alcatel Lucent BGP implementation and its associated operational guidelines. The pressure to implement a fix quickly can lead to overlooking crucial validation steps, making careful judgment paramount. Correct approach analysis. The correct approach involves a phased implementation and rigorous testing. This aligns with best professional practices for network change management, emphasizing risk mitigation. Specifically, it involves 1. Thorough impact analysis, understanding how the proposed policy change will affect existing routing paths, convergence times, and potential traffic shifts. 2. Lab testing, replicating the production environment in a lab to test the policy change under various conditions without affecting live traffic. 3. Staged rollout, implementing the change on a small subset of network devices or in a non-critical segment of the network first. 4. Monitoring and validation, closely observing network behavior and performance metrics after each stage of the rollout to detect and address any anomalies. This methodical approach minimizes the risk of widespread outages, ensures service continuity, and demonstrates due diligence in network management, adhering to implicit operational guidelines that prioritize stability. Incorrect approach is analysis, implementing the change directly in the production environment without prior testing or a staged rollout is a significant regulatory and ethical failure. It violates the principle of responsible network operation, which mandates minimizing service disruption. This approach demonstrates a lack of foresight and risk assessment, potentially leading to a severe outage that could have been prevented. Such an action could be seen as a breach of service level agreements, SLAs, and a failure to uphold professional standards of care in network engineering. Implementing the change only after a brief discussion with a colleague, without any form of testing or impact analysis, represents a failure to follow established operational procedures and a disregard for the potential consequences. This ad hoc decision-making process is unprofessional and increases the likelihood of unintended negative impacts on the network. It bypasses critical validation steps that are essential for maintaining network stability and reliability. Proceeding with the change based solely on a vendor's recommendation without independent verification or understanding of the specific network context is also a professional failing. While vendor recommendations can be valuable, they must be evaluated against the unique characteristics and requirements of the deployed network. Relying solely on external advice without internal validation can lead to misconfigurations or unforeseen interactions with existing policies, resulting in network instability. Professional reasoning. Professionals should employ a structured decision-making framework for network changes. This framework typically includes 1. Problem identification and analysis. Clearly define the issue and its root cause. 2. Solution generation. Brainstorm potential solutions. 3. Impact assessment. Evaluate the potential positive and negative consequences of each solution, considering technical, operational, and business impacts. 4. Risk assessment. Identify and quantify the risks associated with each solution. 5. Solution selection. Choose the solution that offers the best balance of effectiveness, risk, and feasibility. 6. Implementation planning. Develop a detailed plan for deploying the chosen solution, including rollback procedures. 7. Testing and validation. Rigorously test the solution in a controlled environment and monitor its performance post-implementation. 8. Documentation and review. Document the change and conduct a post-implementation review to capture lessons learned. This systematic approach ensures that decisions are informed, risks are managed, and network stability is maintained. Question 15. Governance review demonstrates that a critical BGP vulnerability has been identified within the network infrastructure, posing a risk to routing stability and data integrity. The operations team is under significant pressure to restore full service immediately. Considering the complexity of BGP configuration and the potential for unintended consequences, which of the following approaches best balances immediate operational needs with long-term network security and compliance? Option A. Ignore the vulnerability for now, as BGP configuration changes are complex and the risk of introducing new issues outweighs the perceived threat. Option B. Apply a generic security patch to all network devices, assuming it will address the BGP vulnerability without specific testing on the BGP implementation. Option C. Implement an immediate, unverified workaround to restore service, deferring a detailed risk assessment and remediation to a later, less critical period. Option D. Conduct a rapid, documented risk assessment to understand the exploitability and potential impact of the vulnerability, and then develop and test a phased remediation plan before full deployment. The correct answer is D. Conduct a rapid, documented risk assessment to understand the exploitability and potential impact of the vulnerability, and then develop and test a phased remediation plan before full deployment. Explanation. Scenario analysis. This scenario presents a professional challenge because it requires a network engineer to balance the immediate need for network stability with the long-term implications of security vulnerabilities. The pressure to restore service quickly can lead to shortcuts that bypass established risk assessment protocols. The challenge lies in making a decision that is both operationally sound and compliant with the organization's security governance and the regulatory framework governing network operations, which in this case is implicitly tied to the Alcatel Lucent BGP 4A0-102 syllabus context, implying adherence to industry best practices and potentially specific service provider regulations regarding network security and resilience. Correct approach analysis. The correct approach involves a structured risk assessment that prioritizes understanding the potential impact of the identified BGP vulnerability. This aligns with best professional practice by ensuring that any mitigation strategy is informed and proportionate. By documenting the vulnerability, assessing its exploitability and potential impact on network stability and security, and then developing a phased remediation plan that includes testing and validation, the engineer upholds the principles of due diligence and responsible network management. This approach is justified by the need to prevent future incidents, maintain service integrity, and comply with any implicit or explicit regulatory requirements for proactive security management and incident response within the scope of the 4A0-102 syllabus. Incorrect approaches analysis. Implementing an immediate, unverified workaround without a thorough risk assessment represents a significant regulatory and ethical failure. This approach bypasses the established governance framework, potentially introducing new, unforeseen risks or failing to adequately address the root cause of the vulnerability. It demonstrates a lack of due diligence and a disregard for the potential consequences of an incomplete or ineffective fix, which could lead to service disruption, security breaches, or non-compliance with operational standards. Ignoring the vulnerability due to the perceived complexity of BGP configuration changes is also professionally unacceptable. This passive approach constitutes negligence. It fails to address a known risk, leaving the network exposed to potential exploitation. This directly contravenes the ethical obligation to maintain a secure and reliable network and could lead to severe regulatory penalties if the vulnerability is exploited and causes a significant incident. Applying a generic security patch without considering its specific impact on the BGP implementation is another failure. While seemingly proactive, this approach lacks the necessary specificity. It could inadvertently destabilize the BGP routing process, leading to widespread connectivity issues. This demonstrates a failure to understand the intricate nature of BGP and the importance of context-specific risk assessment, violating the principle of competent professional practice. Professional reasoning. Professionals facing such situations should employ a systematic decision-making process. First, they must understand the immediate operational context and the pressure for rapid resolution. Second, they must consult and adhere to the established governance and risk management framework. This involves a structured risk assessment, identifying the threat, analyzing its potential impact, and evaluating the likelihood of exploitation. Third, they should explore mitigation options, prioritizing those that are both effective and minimize collateral risk. This often involves a phased approach, including testing in a controlled environment before full deployment. Finally, thorough documentation of the process, the decision, and the outcome is crucial for accountability and future learning. This framework ensures that decisions are not only technically sound, but also ethically responsible and compliant with regulatory expectations. Question 16. Examination of the data shows a BGP update received from an upstream provider contains a specific /24 IP4 prefix that is not intended to be advertised to a particular downstream customer peer. The network administrator needs to prevent this specific prefix from being advertised to that customer peer without impacting other routing information exchanged with that peer or other peers. Option A. Apply a blanket inbound filter on all BGP updates received from the upstream provider, blocking all prefixes. Option B. Ignore the BGP update entirely, allowing it to be processed by the BGP process. Option C. Modify the MED multi-exit discriminator attribute of the received route to a very high value before advertising it to the customer peer. Option D. Implement an outbound BGP route filter on the peering session with the customer, specifically denying the advertisement of the problematic /24 IP4 prefix. The correct answer is D. Implement an outbound BGP route filter on the peering session with the customer, specifically denying the advertisement of the problematic /24 IP4 prefix. Explanation. Scenario analysis. This scenario presents a common challenge in BGP routing where a network administrator must decide how to handle a specific route advertisement. The challenge lies in balancing network stability, performance, and adherence to established routing policies. Misinterpreting the implications of route manipulation can lead to suboptimal routing, network loops, or even denial of service for certain destinations. The administrator must consider the impact of their decision on upstream and downstream peers, as well as the overall health of the Internet routing table. Correct approach analysis. The correct approach involves understanding the specific attributes of the BGP route advertisement and applying the appropriate policy based on the network's operational requirements and established best practices for BGP route filtering. In this case, the goal is to prevent the advertisement of a specific prefix to a particular peer, ensuring that traffic destined for that prefix does not traverse the administrator's network unnecessarily or in an undesirable manner. This aligns with the principle of maintaining a well-behaved and efficient routing environment, which is implicitly supported by general network operational guidelines that emphasize control and predictability in routing. Incorrect approach is analysis. One incorrect approach would be to ignore the route advertisement entirely without any filtering mechanism. This would lead to the prefix being propagated to the peer, potentially causing routing issues if the peer's path to that prefix is suboptimal or if the administrator's network is not intended to be a transit provider for that specific prefix. This failure to exercise control over advertised routes is a direct contravention of responsible network administration. Another incorrect approach would be to apply a blanket filter that blocks all routes from the peer. While this might prevent the problematic prefix from being advertised, it would also disrupt legitimate and necessary routing information, leading to widespread connectivity issues and a failure to fulfill the network's role in the global routing system. This is an overly aggressive and indiscriminate action that disregards the need for granular control. A third incorrect approach would be to modify the BGP attributes of the route in a way that is not intended to filter it, but rather to influence its path selection in an uncontrolled manner. For example, arbitrarily lowering the local preference without a clear policy objective could lead to unpredictable routing behavior and potential instability, as the peer might then prefer a less optimal path through the administrator's network. This demonstrates a lack of understanding of how BGP attributes affect path selection and a failure to apply them with a defined purpose. Professional reasoning. Professionals should approach BGP route manipulation by first thoroughly understanding the specific route advertisement, including its origin, prefix, and any associated attributes. They should then consult their network's established routing policies and operational guidelines. If a specific action is required, such as filtering or modifying attributes, it should be done with a clear, documented objective and a thorough understanding of the potential impact on their own network and connected peers. This systematic approach ensures that routing decisions are deliberate, controlled, and contribute to overall network stability and efficiency. Question 17. Performance analysis shows that a critical BGP peering session with an upstream provider is exhibiting frequent route flapping, leading to intermittent reachability issues for a significant portion of the customer base. The flapping is characterized by routes being advertised and then withdrawn repeatedly within short intervals. The network operations team needs to quickly identify the cause and restore stable connectivity. Option A. Immediately initiate a hardware diagnostic on the router interface connected to the upstream provider, assuming a physical layer issue is the most probable cause. Option B. Examine BGP neighbor state transitions. Review BGP log messages for specific error codes or warnings related to the peering session, and analyze the as path and other BGP attributes of the flapping routes to identify patterns or inconsistencies. Option C. Reset the BGP peering session with the upstream provider and monitor for a short period, assuming the flapping is a transient network glitch. Option D. Document the flapping event and continue monitoring without immediate intervention, assuming the issue will self-resolve. Correct answer is B. Examine BGP neighbor state transitions. Review BGP log messages for specific error codes or warnings related to the peering session, and analyze the as path and other BGP attributes of the flapping routes to identify patterns or inconsistencies. Explanation. Scenario analysis. This scenario presents a common challenge in BGP network operations where unexpected route flapping is impacting network stability and potentially service availability. The professional challenge lies in quickly and accurately diagnosing the root cause of the flapping without introducing further instability or violating operational best practices. The pressure to restore service quickly must be balanced with the need for a methodical and evidence-based troubleshooting approach. Misdiagnosis can lead to wasted effort, prolonged outages, and potential financial or reputational damage. Correct approach analysis. The correct approach involves a systematic investigation using BGP-specific diagnostic tools and an understanding of BGP attributes and states. This method prioritizes gathering concrete data about the BGP session and the affected routes. By examining BGP neighbor states, looking for specific error messages, and analyzing route attributes, like as path, med, local preference, that might be changing, the engineer can pinpoint the source of the instability. This aligns with best practices for network troubleshooting, which emphasize data-driven decision-making and a thorough understanding of the protocol's behavior. The focus on BGP state and attributes is crucial for identifying whether the issue is with a specific neighbor, a policy configuration, or an external network event. This methodical approach minimizes the risk of introducing new problems and ensures that the resolution addresses the actual cause. Incorrect approach is analysis. One incorrect approach is to immediately assume a hardware failure on the router and initiate a hardware swap without sufficient evidence. This is a premature and potentially disruptive action. It fails to consider the possibility of a configuration error, a transient network condition, or an issue with a neighboring as. Ethically and professionally, resources should not be expended on unverified assumptions, and unnecessary hardware changes can introduce new points of failure or cause further downtime. Another incorrect approach is to simply reset the BGP peering session without understanding why it's flapping. While a reset might temporarily resolve the issue, it doesn't address the underlying cause. If the flapping is due to policy misconfigurations or external network instability, the problem will likely recur. This approach demonstrates a lack of deep analysis and a failure to adhere to best practices for root cause identification, potentially leading to repeated service disruptions. A third incorrect approach is to ignore the flapping, assuming it's a minor, transient issue that will resolve itself. This is professionally negligent. Route flapping can indicate underlying network problems that, if left unaddressed, can escalate and lead to more significant outages, impacting customer services and potentially violating service-level agreements, SLAs. It also fails to proactively maintain network health and stability. Professional reasoning. Professionals should approach such scenarios by first acknowledging the impact and prioritizing stability. The decision-making process should involve 1. Information gathering. Collect logs, BGP neighbor states, and route table information related to the flapping. 2. Hypothesis generation. Based on the gathered data, form educated guesses about potential causes, e.g., configuration error, neighbor issue, upstream problem. 3. Testing and verification. Systematically test hypotheses using BGP diagnostic commands and by observing changes in BGP states and attributes. 4. Resolution. Implement the solution that directly addresses the verified root cause. 5. Validation. Confirm that the flapping has stopped and the network is stable. This structured approach ensures that actions are deliberate, evidence-based, and focused on achieving a lasting resolution while minimizing risk. Question 18. Quality control measures reveal a persistent BGP flap with a critical upstream provider. The network administrator is under significant pressure from the operations team to restore full connectivity immediately to avoid customer impact. The administrator considers temporarily modifying the BGP import policy to accept all routes from this provider until the root cause can be fully investigated, or, alternatively, disabling BGP session monitoring for this specific peer to stop the alerts. What is the most professionally responsible course of action? Option A. Disable BGP session monitoring for the affected peer to stop the alert notifications and reduce immediate pressure. Option B. Escalate the issue to a senior engineer without attempting any immediate troubleshooting steps. Option C. Investigate the root cause of the BGP flap and address it directly, while communicating the ongoing issue and expected resolution timeline. Option D. Temporarily modify the BGP import policy to accept all routes from the affected provider to restore connectivity quickly. The correct answer is C. Investigate the root cause of the BGP flap and address it directly, while communicating the ongoing issue and expected resolution timeline. Explanation. Scenario analysis. This scenario presents a professional challenge because it involves a conflict between immediate operational needs and the long-term integrity of network routing policies. The network administrator is under pressure to restore service quickly, but doing so by bypassing established BGP policy enforcement mechanisms could introduce significant security vulnerabilities and routing instability. The ethical dilemma lies in balancing the urgency of service restoration with the responsibility to maintain a secure and predictable network environment. Adhering to best practices and potential regulatory compliance requirements related to network stability and security. Correct approach analysis. The correct approach involves diagnosing the root cause of the BGP flap and addressing it directly, rather than implementing a temporary workaround that bypasses policy. This aligns with the principles of responsible network engineering and adherence to established operational procedures. By investigating the underlying issue, the administrator upholds the integrity of BGP policies, which are designed to prevent unauthorized route advertisements, ensure routing stability, and maintain network security. This proactive and systematic approach minimizes the risk of introducing new problems and ensures long-term network health, which is implicitly expected under general telecommunications operational guidelines. Incorrect approach is analysis. Implementing a temporary BGP policy to accept all routes from the affected peer, even if it temporarily restores service, represents a significant ethical and professional failure. This action directly undermines the purpose of BGP policy enforcement, which is to filter and validate incoming routes to prevent malicious injections or routing loops. Such a bypass creates a vulnerability that could be exploited by attackers to redirect traffic or disrupt network operations, potentially violating service-level agreements and general telecommunications operational standards that mandate secure and stable network operation. Similarly, disabling BGP session monitoring for that peer, while seemingly addressing the alert, is a failure to identify and rectify the actual problem. It masks the symptom without curing the disease, leaving the network exposed to the original issue and any potential downstream consequences. This approach demonstrates a lack of diligence and a disregard for proactive problem-solving, which is contrary to professional network management expectations. Professional reasoning. Professionals facing such a situation should follow a structured troubleshooting and decision-making process. First, they must prioritize understanding the problem by gathering all available logs and diagnostic information related to the BGP flap. Second, they should consult established network operational procedures and documentation for handling BGP instability. Third, they should evaluate potential solutions based on their impact on network security, stability, and adherence to policy. Temporary workarounds that compromise security or policy should be avoided unless absolutely necessary and accompanied by a clear plan for immediate remediation of the root cause. Finally, clear communication with stakeholders regarding the issue, the chosen resolution path, and any potential risks is crucial. Question 19. Analysis of a network engineer's proposed implementation of a new BGP policy to influence outbound traffic engineering for a large enterprise network. The engineer intends to directly apply the policy to a live production router without prior simulation or validation in a lab environment, citing time constraints and confidence in the policy's logic. The policy aims to prioritize certain customer traffic flows based on their contractual service levels. Option A. Implement the new BGP policy after thorough simulation in a lab environment, followed by a staged rollout to production routers with continuous monitoring and a documented rollback plan. Option B. Directly apply the new BGP policy to the production router immediately to address the time constraints, assuming the policy logic is sound and will not cause adverse effects. Option C. Rely on the default BGP policy settings provided by the router vendor, as these are generally robust and designed for broad applicability. Option D. Apply the new BGP policy to a single, non-critical edge router first, and if no issues are observed after a short period, then proceed with a full production rollout. The correct answer is A. Implement the new BGP policy after thorough simulation in a lab environment, followed by a staged rollout to production routers with continuous monitoring and a documented rollback plan. Explanation. This scenario presents a professional challenge due to the critical nature of BGP routing policies in maintaining internet stability and adhering to service-level agreements, SLAs. Misconfiguration or improper policy application can lead to widespread network disruptions, impacting revenue and reputation. The core of the challenge lies in ensuring that BGP policy enforcement aligns with both technical requirements and regulatory expectations regarding network neutrality and fair peering practices, as implicitly governed by telecommunications regulations that mandate non-discriminatory access and service provision. The correct approach involves a meticulous, documented, and validated process for implementing and verifying BGP policy changes. This ensures that all routing decisions are predictable, auditable, and compliant with the overarching regulatory framework that expects reliable and accessible network services. Best professional practice dictates a phased rollout, thorough testing in a lab environment, and post-implementation monitoring to detect any deviations from expected behavior. This aligns with the regulatory expectation of due diligence in network operations. An incorrect approach of directly applying a new policy to a production router without prior testing or validation represents a significant regulatory and ethical failure. It demonstrates a disregard for the potential impact on network stability and service availability, which could be construed as a breach of the implicit duty of care owed to customers and other network operators. Its failure to exercise due diligence can lead to regulatory scrutiny and penalties for noncompliance with service provision standards. Another incorrect approach, that of relying solely on vendor default configurations for policy enforcement, is also professionally unacceptable. While vendors provide tools, the responsibility for defining and implementing specific routing policies that meet operational and regulatory requirements rests with the network operator. Relying on defaults ignores the unique traffic engineering needs and compliance obligations of the specific network, potentially leading to unintended routing paths or discriminatory treatment of traffic, both of which are regulatory concerns. The professional decision-making process for similar situations should involve a structured risk assessment of any proposed BGP configuration change. This includes identifying potential technical impacts, evaluating compliance with relevant telecommunications regulations, even if not explicitly BGP specific, they govern service provision, and defining clear rollback procedures. A change control process that mandates peer review, lab testing, and staged deployment is essential. Continuous monitoring and auditing of BGP behavior against established policies and regulatory expectations are also critical components of responsible network management. Question 20. Governance review demonstrates that several BGP routing policies on Alcatel Lucent routers have deviated from the documented best practices and established operational guidelines. What is the most appropriate immediate next step to address these deviations? Option A. Implement new, more restrictive BGP policies across the entire network to prevent future deviations. Option B. Document the deviations and schedule a review for the next quarterly network operations meeting. Option C. Conduct a comprehensive impact assessment of the identified policy deviations on network stability, traffic flow, and peering relationships. Option D. Immediately revert all identified deviated BGP policies to their last known stable configurations without further analysis. The correct answer is C. Conduct a comprehensive impact assessment of the identified policy deviations on network stability, traffic flow, and peering relationships. Explanation: scenario analysis. This scenario presents a professional challenge due to the inherent complexity of BGP routing policies and their potential impact on network stability and service availability. A governance review highlighting deviations from established best practices necessitates a proactive and thorough impact assessment. The challenge lies in accurately identifying the scope of the deviations, predicting their downstream effects on traffic flow, peering relationships, and potential security vulnerabilities, all while adhering to the strict operational and security guidelines mandated by the 4A0-102 Alcatel-Lucent Border Gateway Protocol framework. Misjudging the impact could lead to service disruptions, financial penalties, and reputational damage. Correct approach analysis. The correct approach involves a systematic and detailed analysis of the identified BGP policy deviations. This includes examining the specific configuration changes, their intended purpose, and their actual implementation. A thorough assessment would involve simulating the impact of these deviations in a controlled environment or using network analysis tools to predict traffic path changes, potential route flapping, and the likelihood of unintended prefix advertisements or withdrawals. This aligns with best professional practice by prioritizing network stability and adherence to the operational integrity principles embedded within the 4A0-102 framework. It ensures that any necessary remediation is targeted and effective, minimizing risk to the live network and its users. Incorrect approaches analysis. Ignoring the governance review findings and continuing with the current configuration represents a significant regulatory and ethical failure. It demonstrates a disregard for established operational procedures and risk management protocols, potentially violating internal policies and industry best practices for network management. This approach risks cascading failures and service outages, directly contravening the principles of network reliability and security. Implementing immediate, broad-stroke configuration changes without a proper impact assessment is also professionally unacceptable. This approach lacks the necessary due diligence and could introduce new, unforeseen problems. It fails to acknowledge the interconnected nature of BGP routing and the potential for unintended consequences, leading to further instability and a violation of the principle of least privilege and controlled change management. Focusing solely on the immediate symptoms of any observed routing anomalies without investigating the root cause, the policy deviations, is another failure. This reactive approach does not address the underlying governance issue and is likely to lead to recurring problems. It neglects the proactive risk mitigation required by robust network governance frameworks. Professional reasoning. Professionals facing such a situation should adopt a structured decision-making process. First, thoroughly understand the scope and nature of the deviations identified by the governance review. Second, engage in a detailed impact assessment, utilizing available network analysis tools and simulation capabilities to predict potential consequences. Third, develop a remediation plan that prioritizes stability and minimizes risk, including rollback procedures. Fourth, communicate findings and proposed actions to relevant stakeholders. Finally, implement changes in a controlled manner, followed by rigorous verification and ongoing monitoring. This systematic approach ensures compliance with regulatory frameworks and upholds professional responsibility for network integrity.